everyone. We'll get started here in a few minutes. I just put up some problems here for you to mess with while we're waiting. Do not expect you'll get through all of these, but we'll probably wait till, I don't know, another minute just to let people get here. Supposed to have 22 students and there's 15 of you here now, so.
Good morning.
Morning, Josh. We'll get started. Joshua, we'll get started in just a minute.
Sure thing.
All right, good afternoon, everyone. Welcome to Cal 2. If you watched the orientation video already, then you know who I am. If you have not, then make sure that you do. It's on our Canvas page. Let me bring that up. Maybe. Let me see here. Oh, by the way, I sent out a survey. So far, I had 76 students respond out of like 120 something that I have this semester. It was really about whether or not I should move some office hours or not. And it looks like 81% of the class wants me to keep my 4 to 5 o'clock time slot. So I think it's probably going to stay the same unless something dramatic happens here. But just keep in mind that if you need to get in touch with me, you know how. I've given you my cell phone number. So watch the orientation video. Let me bring that up. So I assume everyone can get into Canvas. Come on. Here we are, Cal 2, section 7. All right, so here's our main page. Orientation video is right there if you haven't watched it. Of the students who've watched it, actually, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12 students have submitted the assignment that I gave for that. 12 of 22. So I don't know if that means that there's still, 10 students that didn't watch it or didn't completely watch it. I'm not sure. But for those of you who did submit it, what you did is correct. Like I didn't have any issues, so we're good to go. If you don't know what I'm talking about, watch the orientation video entirely. All right. So any questions on the layout of the course or the syllabus, the ebook? Are y'all able to get to the ebook, or is it still giving you temporary access? Arturo's saying you're good. You're good, Eduardo?
I haven't checked since yesterday, but it was still temporary for me.
Okay. They're
check real
supposed to be fixing it. I don't know if they are, but I wouldn't stress about it. Just don't buy anything. Just make sure you don't purchase anything.
Last semester, I went through that same, like one of my teachers had that program. Just let the days run out and just keep on accessing it from the actual Canvas. You should be able to access it even after the temporary access. Yeah,
don't do anything. Just let it keep going. And if it turns out that you lose access, we'll take care of it. Okay, so there is a difference. I know some of you I had before for Cal 1. Welcome back. And I'm doing it a little different this semester. I am asking you to submit your homework as a PDF on a pretty regular basis. And what I want you to understand about that is, the homework solution videos are out there already. So it's not about, can you copy my answers? I really just want to make sure you're staying true to yourself in terms of attempting the homework, doing your best. If you fall behind, you can't finish the whole thing, just submit what you have. And we'll see how it goes. What I'm trying to do is catch those 5 or 6 students every semester who don't pass Cal 2 because they just don't do their homework. And so here I'm trying to kind of force them to do their homework. And then I can give you feedback in terms of, if your notation is right, if I can legibly read your work. I mean, that is part of this. So we'll see how it goes. You should have a link, like, let me switch to student view. You should have a link over here to upload your homeworks, and it says when they're due. So your first homework assignment is due at midnight, Sunday night, and it's for 3.5. So whatever you do handwritten, just click on the link and submit it as a PDF file. And I'll be honest, I'm not going to sit there and grade them like with a fine-tooth comb, seeing if you got every little thing right. It's more of, I'm just going to open it up, take a look. Yeah, this looks like good work. Yeah, understand? Yeah.
I think I understand.
Okay. All right. So for those of you who've not been in my classes before, the way I'm going to try and do this Zoom is, I'm going to try and call on every student every day. Now, it doesn't necessarily always work out that way. And sometimes I start to fall off the bus there a little bit with it. And I'm going to try and stay real disciplined this semester. And so when I'm in lecture and I'm actually going through problems, I'm going to be calling on you to help get through the problem. And it may be that you have no idea what the next step is. You're stuck, you're lost. That's what I want to hear. I want you to just be like, I don't understand, or I want you to give me that feedback. Don't be worried about, your feelings. I'm not here to embarrass you or anything like that. I promise you, if you're struggling, there's somebody else in the class struggling with you. And the more I help you, the more I help everyone. So just be prepared for that. Your grade is also determined on quizzes and participation includes you having your video streams on during class. And I think I went through that in the orientation. It doesn't have to be every day, 100% of the time, but for the most part, I want to kind of like get to know you. And part of that is me being able to see you, not just your name on a black screen. So, okay. Any questions? Administrative questions? All right, well, I don't want to waste any time. Cal 2 is one of these classes, I call it a sprint marathon, okay? We're going to go very fast, and we're going to do it for the entire semester. So there is a little bit of a let up in the middle, but it's not, we don't ease up in terms of the speed. It's just the difficulty, I think, gets a little bit better in the middle. Just with my experience teaching this, and I've been teaching Cal 2 for now just over 20 years. It's crazy. I can't believe I've been doing it this long. So my experience in Cal 2 is that in the middle, because it becomes a little more visual, students do a little better. So, but then after that ends, then we get to chapter 8 and it becomes, again, a big struggle. So you have to be prepared for this course. If you've heard things about Cal 2 that, it's hard, that's my experience with it too, is that it is usually the hardest of the calculus sequence. Eduardo, have you not heard that? Okay. All right. So yeah, I mean, I'm not going to sugarcoat this or try and paint it into something it's not. This is my favorite class to teach. If I could just teach one class, this would be it. Okay. And it's because there's so much discovery that has to happen here. And to watch a student evolve from a pretty good student to a really good student. I mean, this class, I get to see that semester after semester. So it's an exciting thing. It's a journey though. It's a journey more than any class has ever been a journey for you. It's like you start off and like your idea of what difficult is right now is going to change. It's like where the bar in your mind is going to raise significantly after you're done with this class. And that's what makes future classes easier, is that now your bar is higher. It's kind of like after you've suffered through this, suffering doesn't seem so bad anymore. It's just like, okay, now I'm hardened, you know? I don't have a military background, but I can imagine that soldiers who have actually been in combat, you know, they become hardened. And this is kind of like Cal 2 is that process of hardening you. So, okay. I could keep talking about this. If you are a really, really good Cal 1 student, that should help you, but it is no indication that you're going to do really well in this class. If it's dangerous, if you were really good at Cal 1, almost to the point where you didn't have to put much effort into it, then that can be dangerous in Cal 2, because I have not met a student who has not had to work hard for Cal 2. And so if you're kind of like, everything's come easy to you, now you actually have to work hard. If you're not like ready to switch gears like that, then this class can catch you off guard. And as soon as you're behind, it's really hard to get caught up. It really, really is. So, you know, just go into this with a very positive. I'm not trying to make this sound like dire and like gloom and doom, but you have to go in like hit the ground running, ready for the challenge. You need to be ready to fail at attempts on problems and then be able to like pick yourself up and go at it again. Like you're going to get a lot of things wrong before you start getting them right consistently. And so crumbling up a piece of paper, throwing it to the side and starting over, that's fine. That's normal. That's par for the course. Okay. All right. Any comments? Anyone want to kind of throw some ideas out there, things they've heard or like questions you might have about the class or anything before I start getting in?
So what out of the class, for what we learned, what are some things we can expect to be, for example, my major is computer science. What are some things that we might be able to be better at doing?
So for computer science majors, there's a lot of things in here that are relevant to computer science, but I would say the most useful thing is learning how it is that computers actually determine values of things mathematically. So like when you go to your calculator and you type in cosine of 2, right? So what actually happened, right? Somebody programmed that calculator to spit out the answer for cosine of 2. But what is actually happening? Because all a computer can do is add, subtract, multiply, and divide. Pretty much that's it, right? So how does it know what cosine of 2 is? Well, we're going to learn in chapter 8. They use what's called the power series for cosine. And that is, you can rewrite cosine by cosine can be rewritten as a new function that involves just addition and subtraction of powers. And so you learn that that's the way computers work, right? So when you're programming, you have ways to use mathematical functions in a way that you never knew existed. I can give you just a real basic example here. So get a calculator out if you have a calculator and just type in cosine of 2. I don't even know where my calculator is. I'll use my phone. Make sure you're in radian mode. Let's see here, cosine 2. Am I in radians? Yeah. So I'm getting approximately negative 0.416. Anyone else get that? Yeah. Okay.
That's what I got.
Okay, so what just happened? Your calculator has no idea about a circle and unit circles or cosine. It has no clue what's going on. So instead of that, I want you to, I'm going to tell you this, you're just going to take it on faith right now. I'm going to tell you that this is kind of a glimpse into the future, that cosine of x is actually defined to be, hold on, 1 minus x squared over 2 plus x to the 4th over 4 times 24 minus x to the 6th over, hold on. 6 over 720 plus x to the 8th over 5040 minus, and then it keeps going. There's a pattern here. Let's not worry about the pattern. So what I'm telling you is that the cosine function is really just this function. And so if you type in cosine of 2 on your calculator, just replace these x's with 2's. So if you now go and just do this on your calculator, 1 minus, let's see, 2 squared is 4, so 4 over 2. Plus 2 to the 4th power. What's 2 to the 4th power?
16, I think.
16 over 24 minus now 2 to the 6th power should be 64 over 720. And then plus, and then I could keep going. Let's just do those. Let's just do that. Do that on your calculator. It's going to take you a couple of seconds to do this. But somebody do those first 4 terms on their calculator and tell me what they get.
Negative 0.42 repeating.
Negative? Did you say
Point-
negative? Or
Yeah, negative 0.42 repeating.
222 forever? Okay. So do you all see that that answer is pretty close to that? It's not exactly, but it's close. Yes. This pattern continues, okay? And it goes forever, actually. And so when you type cosine of 2 into your calculator, this is what your calculator is doing. And it stops because it goes forever. It actually stops. Whoever programmed the computer or the calculator has a predetermined place to stop. And so that's what it's doing. It has no idea what a circle is or sine function. It's using this thing that we call a power series. And it turns out that every function you've ever learned has a power series. And we have a way of figuring out what the power series is for any function.
So
And it
as that
requires
power
using the
series,
derivative and things like that. Go ahead.
sorry. So just for example, like as that power series gets longer or more incremental, it's more accurate.
It's more accurate. Exactly. And you know, on your calculator, you can ask it how many, you can tell it how many decimals you want it to go out with the answer. Right? You can change what's called the float. You're basically telling the calculator to go further out in that series. That's what you're doing. So as a computer science major, understanding that you have ways of using a computer to find values of functions makes things very, very useful. I mean, that's the way we use computers to find answers. And in the real world, computers are good enough because even though it's not an exact answer, it's close enough, because even if you're manufacturing ball bearings for an engine, right, you can only be so precise in a manufacturing process. So, you know, maybe four or five decimal places is enough, because that's the precision of your machine, right? It doesn't matter if you go out 1,000,000 decimal places and it's correct, because your machine can only make it so precise. Hope that makes sense. And then there's other things with series, with computer science. You know, it's understanding what the common series are, you know, convergence and divergence of series, but we're kind of getting the carriage in front of the horse if we start talking too much about it. It's useful, let me just say that.
I will say I can definitely see why you said that the difficulty goes back up in chapter 8.
It does go up, yes.
Because these are spooky.
It goes up in 8 because it's usually brand new. Okay, it's like brand new stuff, but people have never seen it before. Most of the time, at least in the United States, if you come out of high school, the most you're probably ever going to see is like, you know, some of the Cal 2 stuff, but maybe not the series. It just depends. But okay, any other questions or comments before we get in? All right, so let me give you a kind of another kind of, this is kind of a random problem that I'm just kind of top of my head come up with. something that you could use Cal 2 for that might be useful, not necessarily computer science. Let's say, I don't know, let's say engineering. You know, if you
Electronics?
have, pardon me?
Electronics, maybe?
We can do that, like electrical engineering. Let me do this one first. This one is more of a physical example. Like, let's say you have a pipe, okay? Well, of course, we can find the volume of a cylinder. Like, that's not hard, right? We have formulas for finding volumes of cylinders. Well, let's say you have two pipes that kind of intersect one another. Now, this is going to be hard for me to draw, but imagine these two pipes come together and form like a T, right? Yes. Now, can you tell me what the volume is of those two pipes? That's a little bit harder because you have a common region where they intersect one another, right? There's this common region. Let me bring something up that'll help us. Give me a second. Where is this thing? There's Fourier series. I'm not talking about that yet. Hold on. There we go. There we go. This will be easier. Okay, so we have two pipes intersecting one another like this, right? And so I want to know the volume of this. The issue we run into is that you have this region right here, that right there. Now there's actually 8 of these regions. There's 4 across the top and then 4 on the bottom. But this region right here is a common volume to both. They both share that volume. Does that make sense? So it can't easily find the volume of both of these together without understanding that there's that common region between them. So is there a way that you could at least determine what that volume is in yellow? That's not an easy thing to do. Without Cal 2, you can't do it. And then another question you could ask would be, let's say you wanted to weld these pipes together and you had to do a weld across here, you know, weld these two. You might want to know the length of that weld, right? Let's say you have to do a bunch of welds for a job and you want to know how much welding that's going to be because you have to pay someone to weld it. You would need to know like the length of that arc, an arc length. And so that would be useful. Anyway, we could keep going. There's a lot of different things we could do with Cal 2. You have to trust that it's valuable. And as we move through the course, I will do applications when I can. The thing you have to keep in mind with Cal 2 is this. Cal 2 is a math course. It's not an engineering class. It's not a physics class, all right? So what we're trying to accomplish here is teaching you what the tools are that you would use in an engineering class, in a physics class, in a chemistry class, right? We're giving you these new tools, and then the way that they're applied can be, you know, really, it just depends on what field you're in, okay? The general idea and mechanics of what we're doing here are important, and then they can be extended into different branches of science and engineering and, you know, computer science, whatever it is. So just keep that in mind. This is a math course, but we will try and do applications as much as possible. All right. I gave some problems here at the beginning for us to look at to start. So I wanted to run through these derivatives to kind of get our brains going again, and to also give you some idea of what my expectation is in terms of what you can do right now. Okay, so like, I'm going to go through these and I'm going to kind of talk about how fast I think you should be able to do this, you know, or whether or not you need to be looking up notes and, you know, reviewing or whatever. So numbers 1, 2, and 3 should take you no time at all. This should just be right out of your mind, right? The derivative of sine is cosine The derivative of cosine is negative sine. The derivative of tangent is? Uh-oh.
Secant squared x, I
Secant.
believe.
Secant
Secant.
squared x. Those three should be right there, okay? Now, the next three, maybe you didn't memorize those, that's okay, but you need to know where they are. And I would just start to maybe try and burn these in. These are on your formula sheets, which you're allowed to have on your exams. And reference sheet 5 here, page 5, has the derivatives of all 6 trig functions right here. And so derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent secant squared. And then here are the others, the other 3. Be aware of that. Learn them if you can. Check, check, check. All right. Now, number 8, everyone here should know number 8 without having to look anything up. Everyone here should know from Cal 1 that derivative of e to the x is itself, and that the derivative of natural log of x is 1 over x. All right. So those are also just kind of like quick. Everything here blocked off in yellow should be no thinking really involved. Now let's talk about 10, 11, 12, and 13. So what I'm doing here is I'm trying to kind of like build out complexity within a derivative. So the first one, you're doing derivative of cosine of 5x, which means you have some chain rule because you have a 5x inside, right? So who wants to, I'll take volunteers today. Who wants to share, but you can only volunteer once.
It'd be the derivative of the outside, so of cosine, so it'd be negative sine x.
So the derivative of this would be negative sine of what?
Negative sine, oh, I'm sorry, of 5x.
Of 5x, okay?
And then you multiply by the derivative of the inside, so that would
Which
just be
is
5.
By 5, okay. So that's your chain rule. You're taking derivative of cosine of something, which is negative sine of it, but then chain rule, you have to take derivative of what's inside, which is where the 5 comes from. And then you can pop that 5 out in front, right, if you wanted to. This would be fine, but I prefer we write it this way. Negative 5 sine 5x. Good. All right, how about 11? Who wants to do 11?
So is that negative 25 sine x?
25, exactly. So negative 25 sine of 5x. The only difference, right? Mohammed, that was you, right?
Yes, sir.
Okay, the only difference between 10 and 11 is that you had a constant out front, right? This constant in front. So you still just took the derivative of this, which was the previous answer, and just multiplied it times 5. Because constants in front come along for the ride and just scale out whatever our derivative was. Okay, good. So the speed at which Ricardo and Mohammed got those, the speed in which they replied to that is about what I expect from a Cal 2 student right now coming in, is that you could do those derivatives with that sort of efficiency. All right, what about 12? Who wants 12? Yeah, so I added something here, right? Now we've got this power. So the way you'd want to look at this problem is that this is really 5. Then you have cosine of 5x to the 5th power. That's really what's going on, right? So if you take this derivative, you have to apply the chain rule starting with the outermost function, which in this case would be that 5th power.
So
Go ahead.
would that be that we'd start by making it that whole thing to the power of 5 times the natural log of the interior? Would we jump to that, or am I
Are you
spacing
talking
out a
like
little?
trying logarithmic differentiation?
Yeah,
You might be able to do logarithmic, but I think you're working harder than you have to. I mean,
Yeah.
this is just a chain rule. It just has a
Oh,
couple of
yeah, it
layers.
could just become 25 to the
Yeah.
fourth.
Okay, so we can bring this out, take the derivative, that's 5 times this 5, that's gonna be 25. And then all of that cosine 5x to what power you said?
To the fourth.
Fourth, okay? So that's bringing this 5 out, all of this to the fourth. And then keep going, right? Then you have to
Yeah,
move
then
inside
it's
to the
then it
derivative.
should just be times negative sine of 5x times 5.
Times negative 5 sine of 5x. Sorry, I'm out of room over here. So that one I don't expect would be super fast, but maybe, you could get it. You just might have to, do some work and crank it out.
It's been a few minutes and I'm a little rusty.
Yeah, I know. You're all on a break, had a break and. All right. And then 13, well, that's a product rule. Because now I put an X next to the 5. So you've got to do a product here. I'm going to leave that one to you to play with. All right. I don't expect that that would be super fast, but I do expect you could get this. All right. So you do that on your own. That was just a little warm up to kind of get us thinking derivatives again. So what is Cal 2 really about? What is it? What does this course entail? Can I move on? Can I get off the screen? No good. So to talk about Cal 2, I think we should first start by just reviewing quickly what the main ideas of Cal 1 were. So for Cal 1, if you were to try and kind of recap what it was, what would be the main topics from Cal 1?
Differentiation.
Okay, derivative, right?
Limits.
Integrals.
Limits. Okay, integrals. All right. So that's Joshua, right?
Yes.
Okay, so how much integrals did you see in Cal 1?
I saw a bunch and I only cheated on the natural log ones.
Okay, so if you've seen integrals already in Cal 1, that's good. You're kind of ahead of the curve here, because I'm going to start this class out with just like you've never seen an integral before. All right, so that's where I'm going to start. So if you've seen integration, you're already ahead of the game. The question would be, how much have you seen? All right, so this right here, I'm going to put a question mark because you may or may not have seen much integration in Cal 1. Just depends. What else in Cal 1 did you learn? Derivatives, limits.
I can't
What
remember
was-
the name of it, but it was f of x plus h minus f of x over
Limit definition.
Yeah, that's the
Okay.
limit. Yeah, that's the limit definition of the derivative. Exactly, f prime of x.
and then the other thing was I don't remember the name of this one either, but it was like it was a point and then you had an ellipses around the point on a graph, but there was they covered it really briefly.
I'd have to see that to be sure what you're talking about. What are the things that were like you did not enjoy in Cal 1? What were some of the topics that were like the harder things?
Graphing, using the Cal 2. I mean, using the second derivative of Cal max mins and like graphing.
Yeah, to graph by hand. Okay.
Yeah.
Yeah. So that's brutal, right? That's brutal.
There was continuity, I remember.
Continuity. How about this? Usually everyone's like ready to fire this out. Related rates.
I kind of blocked that from my memory.
You blocked it out, yeah. Related rates. A spherical balloon is being inflated so that the volume is increasing at 30 cubic centimeters per minute. At the exact instant, the radius of the balloon is 10 centimeters. How quickly is the radius increasing? Something like that, right? Those were word problems. They were usually a trouble, right? And then we had optimization. That's where you're trying to find like the max and min of functions. So the basic idea of Cal 1, if I were to just summarize it in one quick graph, is that if we have a function, right? That in Cal 1, what we can do is what we learn to do is we can go to any arbitrary point, X. We can go here to the point on the graph, and we can find the slope of that line. And that's what we call the derivative of that function at X. We can find the slope of a tangent line to a graph at any point using the derivative. Right? That's the basic like visual idea of Cal 1. All of it is somehow connected to this. Now, Cal 2, okay, Cal 2. Oh, you know what I should point out also is that when you're learning derivatives, right? When you're learning derivatives, you learn the power rule, right? The power rule, the product rule, the quotient rule, and the chain rule, right? Those are the rules you have to get good at: power rule, product rule, quotient rule, chain rule. And the good thing about those rules is that they are very mechanical. Like the power rule is pretty much, I mean, bring the power down, subtract 1 from the power, right? The product rule, there's a formula for it. The quotient rule, there's a formula for it. The chain rule is a little weird, but there's still a procedure, right? That's very mechanical, methodical, as long as you can kind of see the composition of functions. Cal 2 doesn't work that way. I'm not going to fill you with a bunch of formulas and have you do these formulas just like you did in Cal 1. It's more complicated than that. So unfortunately, we won't have that same sort of flavor in this class. We'll have methods for doing things, but we won't have just kind of like, oh, here's the new rule. Just use it every time you see this. All right, Cal 2. So I'm going to just real quick, in a nutshell, what is Cal 2 about? 3 sections: antiderivatives, that's the first third of the class. The second is going to be applications. Of antiderivatives. And then the third is going to be series. That's the main 3 ideas for Cal 2. Antiderivatives is basically us taking a bunch of time trying to figure out how to undo a derivative. So if somebody, asks you to take a derivative, that's fine. But what if they give you something and ask you to go backwards? Okay, so we're going to spend a lot of time figuring out how to do that. After that, we're going to see how we can use it. How do we use that? What's the usefulness of being able to do an antiderivative? And then after that, we'll move on to series. And that's where, like cosine, I was showing you that cosine thing. That's the basic 3 components of Cal 2.
Good question.
Yes.
Aren't antiderivatives integrals? Aren't those the same thing?
They're connected, yes.
Oh, okay. Is there like a hard difference or?
Antiderivative is just any function that when you take its derivative, you get some original function. The integral can represent 2 different things. It can represent that, or it can actually represent the area underneath the curve. It depends on if we're talking about a definite integral or an indefinite integral, which at this point, I'm assuming a lot of you haven't seen, so I'm not going to get too much into that.
Yeah.
But yeah, there is a slight difference between antiderivative and integral.
Okay, gotcha.
All right, so the first beginning of this class is about antiderivatives. That's going to be a major part of the beginning third. And before we get to that, we need to kind of finish off some stuff from Cal 1 that you didn't necessarily see in Cal 1. And that is, it goes back to where I started today with these examples. I asked you for the derivatives here. These first 6 problems I gave you, were the 6 trig functions. Those were the 6 trig functions that you learn in pre-cal, right? You learn about sine, cosine, tangent. You learn about those in pre-cal. And then in Cal 1, you learn what their derivatives are. But in pre-cal, there's another 6 trig functions you learned. And they were the inverse trig functions, right? Remember that in pre-cal, you learned that all of these functions have inverse functions, don't they? Functions that undo them. Well, we need to make sure we understand that each of those inverse functions also have derivatives. And we need to figure out what those derivatives are. So that's where we will start today. We're going to talk about the inverse trig functions and their derivatives. Then we will move on and eventually get into antiderivatives. But we're going to take a step back into Cal 1 for a minute, and then we'll proceed through the course. All right. I could keep talking about what Cal 2 is about, but I think I'm ready to just get in. I apologize. I'm trying to get over something right now, so my voice is all messed up. These notes are all in Canvas. You can access these and print them out if you'd like. So you don't need to worry about, you know, copying all this stuff down. Just go into Canvas, go into files, course notes, and everything is here for this semester. All right. All right, so we're going to talk about inverse trig functions. This first part is review. Okay, this is all review until I tell you. We go back to college algebra and we remember what a one-to-one function is. A one-to-one function is basically a function that passes both the vertical line test and the horizontal line test. So if you have a graph of a function, what is that? Oh, it's not wanting to draw. Oh, there it is. If you have a graph, this is a function, right? That is a function. It passed the vertical line test, but it is not one-to-one because it would fail the horizontal line test, right? So in order to be one-to-one, you got to pass both. So something like, well, that would be one-to-one because it passes both vertical and horizontal. You have to have a one-to-one function to be able to have an inverse. Again, this is back to a college algebra concept. You have to be one-to-one to be able to be invertible, to have an inverse function. So this first part of the note says, if you look at the trig functions from Cal 1, like here's the sine function. The sine function is a function, but it is not one-to-one, because if you draw horizontal lines, you hit it more than once. So what we have to do in order to make the sine function have an inverse is we have to restrict its domain in a way that we get a one-to-one function on some restricted domain. So what we do is we agreed, we being human beings, we agreed that if we cut it off between here and here and just look at this segment right here, that would be one-to-one, just in that little region. So in pre-cal, that's what we do. We define the inverse trig function for sine to be just that piece, right? Well, that's the restriction on the sine function. And if we restrict it, then we can define the inverse. So we define the inverse with its restriction, and we have these relationships between the inverse function and sine itself. So let me just kind of point out how this works, just so to remind you. So if we say, what is sine of pi over 6? To figure out what sine of pi over 6 is, you don't go get your calculator, right? You don't, you should know what that is. The way I do it, I think about a unit circle. I go to pi over 6. That's pi over 6. And then I look, what is the y coordinate there? Because the y coordinate corresponds to sine. The y coordinate here is a half. So the answer is 1/2. How is that related to the inverse sine function? Well, this means that the inverse of sine, the arc sine of 1/2 must be the pi over 6. So they, you know, whatever sine does to pi over 6, whatever it spits out, you take that output and put it into the inverse function, it'll spit back the angle. that look familiar to you all? It should be, I mean, I know it's been a while pre-cal and stuff, but I'm just trying to remind you what the inverse sine function does, that there's some restrictions on its domain. Here's a graph. Here's a graph of both the sine function and its inverse. That's both of them graphed together. And you can see that they are reflections of one another over the identity. So if you draw a perfect diagonal here, any function and its inverse graphed together should be a reflection over the identity, which we can see from that picture. Again,
Isn't
this is all
the-
just review. Go ahead.
Isn't the arc sine function, the sine function rotated 90 degrees and then flipped?
Isn't the arc
Like,
sine?
isn't it that same shape, but it's going up along the y-axis?
You mean like a sine curve up the y-axis?
Yeah,
Not
isn't
the
that
whole
what it
curve.
does?
Not the
Oh.
whole curve, though. Because
Oh,
there's a restriction. You can only look at it
Yeah.
on a restricted domain. So that means the range of it is restricted too.
Okay,
Yeah, so this is it. I mean, this is the complete graph of both. All right, so I'm trying to decide. Yeah, let's just do these. These will be quick. This is pre-cal stuff. So find arc sine of 1 without a calculator. So the way I think about this is this. I say, all right, basically I need to figure out sine of some angle, I'll call it theta, has to be 1. And I want to know what theta is. Joshua, what do you think?
Well, I'm not terribly great at these, so I need to refresh on them, but usually I would look at the unit circle. If I remember correctly, I believe if sine is 0, then it should equal 1.
So when you look at the unit circle, sine corresponds to which coordinate, the x or the y coordinate on the unit circle?
Oh, the theta is the x for sine.
So if you take any point here on the unit circle, if this is the angle theta, the coordinates of that point will always be cosine theta, sine theta, which means the y coordinate is the sine of the angle.
Okay.
So what this is really saying to you, Joshua, is where is the y coordinate equal to 1 on this unit circle? At what point on the unit circle is your y coordinate equal to 1? Isn't that right up there? Straight up?
Mm-hmm.
And what is the angle that corresponds to that?
It's a 90-degree angle.
90 degrees. So our answer here would be either 90 degrees, you would have to put the degree symbol, or in radians, we would put pi over 2. And I would get used to using radians because we use almost exclusively radians in this class.
On the basis of what you were showing us earlier, would you mind scrolling up? Just a bit.
Wait, keep going up.
Right there. That's fine. Because the way that you had the problem before that you're correct, but I did get confused from that point to the next point, which was that you had it seemed like you distributed the problem differently between the two. I don't know what you did different.
I'm not sure I'm following.
Well, because initially the first one you looked like you translated you just put y where x was for the problem above for when you went from sine to arc sine. Here you're about because on the other one it was I think it was arc sine y, but here you're evaluating sine theta entirely as y.
I did this. I wrote sine pi over 6
Yeah,
is 1/2.
yep.
And then I
Right.
wrote, that's the same as saying arc sine of 1/2 is pi over 6.
Is that is that the same process as the example 1 on 3.5?
Well, this is just showing the relationship between sine and inverse sine. That if you take sine of an angle, it's going to spit out a number. So if
Okay.
you take arc sine of that number, it's going to spit back the angle, right? I was just
Sure.
showing the relationship here. Here, we're saying arc sine of a number, and we're trying to figure out what the angle is. So we're saying, since it's sine, we're talking about the y coordinate. We're saying, like I said here, where's the y coordinate?
Mhm.
1? At what angle does that happen? And then you determine the angle is pi over 2 or 90 degrees.
Okay, I'm following now. Okay.
Let's try this one. So let's look at this one, everyone. If I'm doing arc sine, same thing, different notation of √3/2, it's the same question. Where's the y coordinate √3/2? So we go to our unit circle. And where's the y coordinate? Why am I doing y coordinate, not x coordinate?
Because you're using sine.
Because we're doing arc sine, right? If it were arc cosine, we'd be doing the x coordinate, but it's arc sine. So we're going to do the y coordinate. And we're saying, where is the y coordinate √3/2? So you've got to know this, right? You've got to
Pi
know
over
this. Where is it?
Pi over 3, I believe.
Pi over 3. So that's what, here?
And 2 pi over 3, I believe.
Yeah, that's this. The x coordinate's 1/2. That's not relevant, but, and then also here, right? That also has the same y coordinate, doesn't it? Right. So which of the two answers is it? And why? Lewis, you're pointing to the right. Lewis is saying it's this one.
It's not in the domain.
It's not a domain. Okay, so when we define the arc sine function, remember said that in order to define the arc sine, we have to restrict sine between -pi/2 and pi/2. So our answers, when we're down here looking at this problem, right? When we're trying to work this, we are actually not allowed to even look. Hold on. There we go. Okay, we are not even allowed to look over here. We can only look between pi/2 and -pi/2. Our answer can only live in these two quadrants. So it must be this one, which means our answer must be pi/3.
This is when we're looking at inverses, you said?
Inverse sine.
Inverse sine.
Inverse sine has a restriction between -pi/2 and pi/2. So
I
I
realize
realize
this
this
learn
is a
the
lot.
unit circle?
Wait, go ahead, Joyce. Sorry.
Oh, how do we learn the unit circle? Because I wasn't very familiar with it.
Come to my office hours.
Okay.
I will be happy. If any of you did not learn your trig functions off a unit circle and like memorize some table or something like that, come to my office hours. We'll spend 20 minutes. Once you understand the unit circle, your life becomes so much easier with trig. It really does.
And these restrictions are only for inverses, right?
Yes, and each trig function has a different restriction.
Yes.
So arc sine has a restriction between -pi/2 and -pi/2 and pi/2. Anyone know what the restriction is for inverse cosine?
Is it 0 to pi?
0 to pi. And then tangent has an inverse.
It's the same thing with sine.
Same thing as sine, but without the endpoints.
Yeah, you can't equal to.
So -pi/2 to pi/2. So look, this is all here. I'm reviewing it right here in this next note. Say, hey, look, we do the same thing with cosine. We have a restriction. The restriction is between 0 and pi. Then we can define the inverse. And then for tangent, we have a restriction between -pi/2 and pi/2. Oop, I need to take out the inequality. That's a strict. That's a typo. I don't know why I never saw that before. For tangent inverse, you cannot include the endpoints. Tangent's not defined at these 2 points. So look, here, let me kind of I don't want you to start like going crazy because I've come in here and this is a bunch of stuff in pre-cal you don't remember. All right. Here's what I want you to take away from this. Every trig function from pre-cal, sine, cosine, tangent, all the reciprocal functions, secant, cosecant, cotangent, they all have inverse functions if we do correct domain restrictions. That is a pre-cal concept. You can go review it if you'd like, okay? I'm not going to test you on that. That's not what we're interested in here, though. We have 6 new functions. They're the inverse functions. We want to know what the derivatives of those functions are. Okay, in pre-cal, we established that there exist these inverse functions. Here, we're going to just talk about, well, what are their derivatives? If they're functions, I should be able to find the slope of a tangent line, shouldn't I? So how? What's the derivative? So that's what I'd like to get into now. This is the main part, the heart of what's important in this section, the derivatives of the inverse functions. So to do this, to find the derivative of an inverse function, I'm going to need 2 things. Right now, when we're done here today with the derivatives of these inverse functions, you are going to be able to go to your formula sheet and just look them up. Like, you're not going to have to absolutely have these completely memorized in the next day. All right, you'll be able to reference them. They're right in your formula sheets. Okay, so here were the 6 derivatives of the trig functions from pre-cal. You learned that in Cal 1. Right below that is what I'm about to show you today, are the derivatives of the 6 inverse trig functions. Okay, that's what we're interested in today. Once I prove to you that these are the derivatives, you will never have to prove that to me again. But the reason I'm showing you the proof is because what I do when I'm showing you is something we're going to use later. Like, the actual procedure is very important. And so that when we do some other stuff that's harder later, you will have seen this before. So I don't want you to just sit here and be like, oh, well, you know what? I'm going to be able to look those formulas up later. Who cares? Okay. Pay attention to how I get these. I'm about to prove these. I'm about to prove formula 19, 20, 21, 22, 23, and 24. I'm going to prove that this is true. All right. So here we go. I want to prove now what the derivative of inverse sine is. Let's do it. So if y equals the inverse sine of x, find y prime. Okay, just take a deep breath. Think about what I'm asking you. I'm asking you to find the derivative of a function that you've never really tried to take the derivative of before, right? We know this function exists. It's an inverse function from pre-cal, domain restrictions aside. What's its derivative, right? So you can't use any rule that you learned in Cal 1. There's no rule like you just don't know what the derivative of this is, right? So you ready for me to show you? I'm going to show you how I'm going to go about this. First step, I don't know anything about this, so I'm going to be clever. I'm going to take sine on both sides of this. All right. Now, the reason I did that is because if I take sine of sine inverse on the right side, what will happen when you put sine together with its inverse?
Don't they cancel each other out?
Cancel each other out. So what will be left on the right side?
X.
X, okay? And on the left side, we have sine of y. Yeah, that seemed pretty straightforward. Now, I've not determined what I'm looking for. I'm trying to find y prime, right? That's what I'd like to know. What's y prime? Here's what I know so far. Sine of y is x. That doesn't tell me what y prime is, though, right? So here's the cool part. What I'm going to do now is I'm going to differentiate both sides of this equation implicitly with respect to x. Okay, this is Cal 1. I'm going to be taking the derivative on the left side of the equation with respect to x. And I'm going to be taking the derivative on the right-hand side of the equation with respect to x. So let's start with the right side, because the right side is the easier of the two. Oh, I'm going to say this wrong. Maiki? Am I saying that right?
Miyaki.
Wait, say it.
Miyaki.
Miyaki. Okay, hold on. Miyaki. Okay, Miyaki. All right, Miyaki. Putting you on the spot here. Cal 1, the derivative with respect to x of x.
Would be 1.
1. Okay, good. Right? That's basically dx dx, which is just 1. Good. Let's keep going, Miyaki, since you did so good there. How about the derivative of sine of y? So Miyaki, what's the derivative of sine of anything?
So
What's that?
is it 0?
No. So Miyaki, what's the derivative of sine of x?
Sine of x? Or is this be, I mean cosine, yeah.
Yeah, cosine. Okay, yeah. So,
Sorry. Yeah.
so the derivative, it's all right. See, when I put you on the spot, it makes you nervous and makes you
Yeah.
like, that's good though. Okay. The sooner we get like through our nerves, the better, because isn't that what always messes you up on tests? Your nerves get the best of you.
Yes.
So let's,
Yeah,
there's no shame in a class like this. All right. Nobody's going to leave here and be like, Miyaki, man, like, oh man. All right. This is between us. We're all in this together. All right. So Miyaki, the derivative of sine of something is cosine of it. So I'm going to put cosine of y.
Right.
But because we're differentiating with respect to x and our variable is y, we have to then apply the chain rule and multiply it by the derivative of y with respect to x, which is just y prime, isn't it? This is chain rule in what's called implicit differentiation. Does that all look familiar to you all? If not, this is where you make a little asterisk, come to my office hours and like, what the hell are you talking about? Now, you might have seen this left as dy dx in your Cal 1 class. I'm just going to change it to y prime, the same thing. So I've applied the chain rule on the left side, and then on the right side, derivative of x with respect to x was 1. Okay, this is good. Do y'all see y prime here? That's what we're trying to solve for. So now what I'm going to do is divide both sides by cosine y. Very good. Yes. Y prime, the derivative of this function so far is 1 over cosine of y. There's a problem here. The original function or original equation was y is some function of x, right? Arc sine of x. And our answer has y in it, not x. So what I'm going to do now is get it back to x. And the way I'm going to do this, and this is the technique that I'm saying we're going to use later, I'm going to go back to this right here. That statement right there. And I'd like for you to think about this. From that, I'm going to draw you a picture. This is a right triangle. I'm going to call the angle in here y. According to that equation, sine of y equals x. I could also look at that as sine of y equals x over 1 because x is x over 1, right? Isn't that what x is? Now, why am I doing this? Just bear with me here. Sine, by definition, SOHCAHTOA, is opposite over hypotenuse, isn't it? Opposite over hypotenuse. So using this relationship, if I finish drawing this right triangle, I can label this side x and this side 1. And do you now agree with me that this triangle is a visual representation of this equation, sine of y equals x? It is, right? It's a visual representation of this. Now, the reason I did that is because I want to know what cosine of y is, don't I? Cosine of y? And if I have a triangle that has y as the angle, and I want to know what cosine of y is, the only thing I need to determine is what the adjacent side is. If I know what the adjacent side is, then adjacent over hypotenuse would be cosine, yes? I can get that side by solving for it because I have a right triangle. I know 2 of the 3 sides. So why don't we call this side A? And let's use Pythagorean. A squared plus x squared is 1 squared. That's just Pythagorean on this triangle. That's a squared equals 1 minus x squared. So all I did there was just squared the 1, brought the x squared over. And I'm gonna take the square root on both sides now. When I take the square root on both sides to get a, I'm supposed to do plus or minus. I'm only doing the plus because a is the length of the side of the triangle, so it's not going to be negative. So I'm only looking at the positive answer here. So this side here, a, is the square root of 1 minus x squared. So let's get back to this. Y prime equals 1 over. Well, now you have the triangle. Can you tell me what cosine of y is off this triangle? What cosine of y is?
1 over the square root of 1 minus x squared.
That's what this answer is, yes. I'm saying cosine of this triangle would be the adjacent over the hypotenuse, right?
Yes, yeah.
That's what this is here, which is just square root of 1 minus x squared. And then that answer goes down here. All right.
We never seem to like fail to blow our minds.
Well, I mean, this is the way it's
Seriously.
done. So this right here, this whole process of me drawing this triangle over here, this is what's called creating a reference triangle. And we are going to use this process later quite a bit, creating a reference triangle. We'll be doing it for something different, but the idea is still the same. So in order to do this problem, let's just kind of recap what we did here. We started with a function we didn't know the derivative of, right? We took the inverse on both sides so that we had it in terms of a function we were familiar with, sine. Critical step, implicit differentiation, right? That got us a derivative. We had chain rule in here, we had to be careful. Then we solved for y prime. Our answer was in terms of y. So to get it back to x, we used this equation to create a reference triangle. From that, we were able to determine what cosine of y is in terms of x. Take that answer and stick it back in here, and now we have an answer. So if you go to your formula sheet now, and you look at this formula right here, the derivative of arc sine of x is 1 over the square root of 1 minus x squared. Okay, we just proved that that's true. Make sense? Let's do, well, yeah, let's just leave it like that for now. Because now I want to show you kind of how this works. Now that you know this, okay, now that you know what the derivative of arc sine is, and I'm going to just put it up here so we can reference it. If you take the inverse sine function and you take its derivative, you get 1 over the square root of 1 minus x squared. Okay, that's what we just determined. Now that you have that, we've established that. Now everything you learned in Cal 1 is on the table. which means I can now start using that function, take derivatives of things that involve composition, chain rule, power rule, product rule, quotient rule. Let me explain it. Look at this example. What if I tell you y is equal to arc sine of x squared plus 1. And then I ask you to find y prime. Now what you have to put together from what you learned in Cal 1 is that now you have to apply the chain rule to this, right? We just established this. A minute and a half ago, we established this new formula for a derivative. But now we get to play with pretty much any way you want to build it, you have to be able to take derivatives. So the derivative of this would be, well, we have an inner function here, and then the outer function is this. So chain rule. Start with the outside. What would the derivative of arc sine of this be? Let me see. Let me call on someone. Hunter, you're up if you want to go.
Sure.
Okay.
So shouldn't it be, let me write it so I'm saying it correctly. 1 over the square root of 1 minus, and then in parentheses, x squared plus 1.
Perfect. Okay. Then that's squared, right?
Yes, that's
In
squared.
the formula, whatever your x is, it goes here, but then it also gets squared.
Yeah.
Okay, so yes, you've done the outer layer of the chain rule, and
Yeah.
now you're almost done.
Now we multiply it by the derivative of x squared plus 1, which should just be 2x.
There you go. And you could clean it up.
Put
You
it
could
on
put the
top,
2x on top and maybe slide it over. And then on the bottom, I wouldn't square that. I would just leave it. X squared plus 1 squared. There it is. That's your derivative. So now it's like everything else is fair game. You can start using that function with anything else now, which is, I guess, good and bad. I mean, however you want to look at it. It's good we can do more now, but it's bad that we can have more possibilities here. So I believe in the notes, there's an example here. Why don't you try this one on your own? I'll give you a minute. Give you a couple of minutes to do this one. See if you can find the derivative of that. So Eduardo and Catherine are like the next two that I'm potentially calling on here. Just FYI.
I got it.
Okay. Eduardo, how'd you do?
Well, it doesn't look pretty.
Okay, go for it. What do you have?
Okay, so it's gonna be 1 over the square root of 1 minus, or sorry, it's just gonna be x squared if I'm not wrong.
Okay, so you already simplified it. Let's go back to like what you did and then we'll clean it up. So you had
Yeah.
1 minus,
1 minus the square root, then it's gonna be 1 minus x squared, and then that's parentheses squared.
okay, good. So that's what Eduardo's doing there is kind of the chain rule, the outside, taking care of the derivative arc sine of something. The thing that was inside the arc sine was this, so that got plugged in down here. Good. Continue, because there's more, right?
Yeah, there's more. It's gonna be, and then you're gonna multiply that by the practically the derivative of the square root. So that would be negative x over the square root of 1 minus x squared.
How'd you do that?
So for that one, usually a square root, you would usually do the 1 over 2 times the square root of x. And since you're using the 1 minus x squared, you're canceling out the 2's and you just end up with that simplified.
Okay, so Eduardo is demonstrating to me right now that Eduardo understands chain rule. Like I can see that just by your response. That's excellent. That's good. That's where we want to be. Okay, your life will be so much easier in this class if you understand chain rule. So this is the simplified version of the derivative of this. Eduardo's already done this simplification for us. I'm just going to write down over here though what the derivative of this is.
Mhm.
This is 1 over 2 square roots of 1 minus x squared times the derivative of what's inside, which is negative 2x squared. No, negative 2x, sorry. And then Eduardo, you cancel those 2's out already. Yes? Good. Are we done, Eduardo?
You would just
Other than simplification, are you done with the derivative?
yeah, if I'm not wrong.
This is the derivative. This is pretty much the derivative cranked out. And so I think you squared the square root next and then combine some things together. Okay.
It's just canceling out most of it.
Yeah. Okay, good. I'm going to leave it like this just for now, because again, all I'm trying to do is illustrate the fact that everything you learned in Cal 1 about all the different rules, the only thing we're adding to this now is this new layer of, now we've got these new functions that have their own derivatives. So we have to apply the chain rule and all the other rules to those new derivatives. All right, I have to keep going. I need to prove to you the rest of them, okay? So the next one I want to prove is what the derivative of cosine inverse is. Now, since we just did sine inverse, I'm going to go faster through this one. Okay. So Catherine, since you're up, do you remember what was the first step of when we did arc sine? What was the first thing I did? I think you're muted if you're talking.
Sorry, like, I'm
Okay.
not, I can't remember right now.
Okay, so when you go back and you look at this, the problem we just did, right, with arc sine when I was proving what the formula was, the first thing I did was got rid of the arc sine by doing sine on both sides, right? That kind of killed off the arc sine. Catherine, what do you think I should do here then if I want to kill off the inverse cosine?
The same thing.
Yeah, just with cosine, right, on both sides. Let's do that. So cosine of y, that's the left side with cosine, the right side with cosine. Right? The right side, they kill each other off. You just get x. On the left side, you have cosine y. All right, I have Alec or Caesar. I'm not sure. Is it both? Is it
I just go by Alec.
Alec? Okay, I'm going to change that here. Okay, Alec. Again, referencing kind of what we did before, what do you think would be the next step? So we took sine on both sides, then this step here.
I'm not too sure. Hold on. Let me double check.
It's all right. Who wants to help?
I'll help if that's okay.
Yep, go ahead.
You do the derivatives of both sides
Okay, with respect to
with respect to x, I
with
believe.
respect to x. Okay, so Audrey, do you want to tell me what the derivative of the left side with respect to x would be?
Let's say it's negative sine of, sorry,
Yep, you're good.
negative sine of y, and then the right side's just 1.
Negative sine of y. Okay, the right side just 1.
And then you go to
Uh,
left side times y prime.
You'll have a y prime right here, right? Because of chain rule. You have to take derivative cosine of y, which is negative sine of y, then times the derivative of the y itself, which is going to be y prime. So you have to get that y prime to pop out. Like it has to come from somewhere. So it comes with the chain rule on this. Then we can solve for y prime, dividing both sides by negative sine of y. When it divides both sides by negative sine of y, it turns this into a negative 1 over sine y. Is that clear up to that point, everyone? Got questions? What next?
We use a reference triangle now?
Reference triangle. Okay. Based on what information? What am I going to
Cosine y
use?
equals x.
Cosine y equals x.
Cosine y equals x. I'm going to go draw a reference triangle. So that means I'm using cosine of y equals x. I can look at x as being x over 1 again. The angle inside is y. Cosine is what side over what side? SOHCAHTOA.
Adjacent over hypotenuse?
Adjacent over hypotenuse. That means the adjacent side is x and the hypotenuse must be the 1. So I put an x here and a 1 here. Now this side I don't know, but I need it because I want to know what sine of y is. And sine of y will only come if I can get the opposite side here. So I have to solve for this side. I'll call that side b. I don't know why, I'm just going to call it b. So I need to solve for b. X squared plus b squared equals 1 squared. B must equal, well, I'll do b squared. B squared must be 1 minus x squared. And then b must be the square root of 1 minus x squared. So took the square root on both sides. Once I know what b is, I can figure out what sine of y is. Sine of y should be this b over 1. So it should just be the square root of 1 minus x squared.
So y prime is negative 1 over the square root of 1 minus x squared.
Yes, it is. Negative 1 over the square root of 1 minus x squared. That's very, very close to the previous answer, isn't it? From the previous one for arc sine. If you go check the formulas, the difference between the derivative of arc sine of x and arc cosine of x is that this one has a negative. It's hard to see it. There's a negative right there. Otherwise, they're the exact same answer. I'm going to do one more. And this one that I'm about to do is one of the most important ones. It's going to come up a ton in this class. And that is the derivative of arctangent of x. So if y is inverse tangent of x, and we want to find y prime, my first step is to take tangent on both sides. Doing that so I can kill off the inverse tangent. That gives me tan y equals x. Same thing we did last time, right? Kill off, now implicit. So I'm going to take the derivative with respect to x on the left side and the derivative with respect to x on the right side. The right side's always the easy one, that's 1. On the left side, we have to know what the derivative of tangent is, right? Which we've already learned or refreshed our memories earlier today, but that's secant squared of y. And then chain rule times derivative of y, which is y prime. See, do y'all see this is the same? I'm doing basically the same thing here. And then now y prime is equal to 1 over secant squared y. So I divided both sides by secant squared y. That's my derivative. Reference triangle. Take that. Tangent y equals x over 1. Draw a reference triangle. Y. Now tangent is which side over which side?
Opposite over adjacent.
Opposite. So this opposite side should be x and the adjacent side should be 1. And I'll call this side h for hypotenuse. And I'm going to need to know what h is because don't I need to know what secant of y is? Secant is the reciprocal of cosine. So or you could say secant is hypotenuse over adjacent. Either way, I need to know the hypotenuse. So using my Pythagorean, 1 squared plus x squared is h squared. That gives me 1 plus x squared is h squared. Square root of 1 plus x squared is h. From this, I know this side, I can now tell you what secant of y is. Right, secant should be the hypotenuse over the adjacent. The reciprocal of cosine, right? Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So I'm going to take square root of 1 plus x squared over 1. So I don't really need the 1 on the bottom. That's what secant y is.
So when secant y is 1 plus x squared, or the square root of 1 plus x squared, and
That's
since
what
we have a
secant y is.
so since we have a squared in there, does that cancel out the square root?
Exactly. Over here in our answer here, we had a squared there. So we're going to take this answer and square it and plug it in here. So it's basically this square root of 1 plus x squared squared, which just leaves us with 1 over 1 plus x squared. And that's the derivative. That is in your formula sheets. Again, I'm sure you know where they are, but this one, I'm just again saying this one comes up a lot. So you should know what the derivatives of those 3 are. The next 3 inverse trig functions, I'm not going to prove them to you. All right. So these 3 I just did. These 3 I won't show you. You know that they exist. They don't come up that much in this class. Formulas 22, 23, and 24 don't come up that much. 19, 20, and 21 do though. All right, so we want to be comfortable with those. Let's see here. I have about 10 minutes. So let me show you how we can use this for a problem. Again, this would be almost like a Cal 1 problem. Find the equation of the line which is tangent to this curve at this point 0, 0. So this is the first time I'm going to do this. I'm going to go bring up Desmos. If you've never used Desmos, this is a graphing utility that I recommend you become acquainted with. It's super powerful. Arc sine of x times y squared equals x plus y. And then I'm going to put the point 0, 0. All right, so what I've done here is I have graphed this relationship of this equation. And what this question is asking us to do is to find the equation of the line that's tangent to that curve at the point 0, 0. So I want to know, what is the equation of the line that would be tangent to this curve at this point? What's the equation of that line? Which we learned how to do in Cal 1, right? We have to first find the derivative at that point, which would mean we need the slope of the line. Once we have the slope, we can use the point slope formula to come up with the equation. So I'm going to run through that. So first things first, I'm going to try and find y prime. Now this equation that we have here is an implicit equation. It cannot be solved for y easily. So I'm going to use implicit differentiation on this equation. Let me write the equation down first. All right, here we go. Derivative. I need the derivative with respect to x on the left side. And then the derivative with respect to x on the right side. All right, on the left side, let's see. Jose, have we talked today?
Not yet, sir.
I don't see Jose. Where's Jose? Oh, there you are, Jose.
Can you hear me, sir?
Are you following? Yeah, I can hear you kind of. Are you following this, or do you feel like kind of wobbly here? How do you feel?
The left side kind of wobbly, but the right.
How about the right side?
Yeah, it's just 1 + 1, right?
1 plus. So I agree. The derivative of x with respect to x is 1.
Yeah.
Plus, but what's the derivative of y with respect to x?
Y prime.
Yeah.
That's just y prime. That's not 1. It's y prime. So this is y prime. Or dy dx. It depends on how it was shown to you in Cal 1. You can use dy dx, or you can use y prime. Your choice. So that's the right side. You just do them. You do them individually because there's addition there. But the left side's the problem, right? This is the one that's complicated. But we just learned what the derivative of arc sine of something is, right? The formula for that is that the derivative of arc sine of x is 1 over the square root of 1 minus x squared. That's the formula we just learned. Now, in this particular case, we're doing arc sine of all this junk. So that's kind of taking the place of the x in the formula. And we have to apply the chain rule. So when we differentiate this, the first thing I'm going to write is 1 over the square root of 1 minus, and then whatever was there, xy squared, all of that squared. That's the derivative of the arc sine of this part. But then I have to multiply times the derivative of what's in here, which is going to require what?
Product rule.
Product rule. Right? That's a product. You have a product between these two. So if I do product rule on there, I first have to take the derivative of x, which is 1, times y squared, plus now I have to take derivative of y squared with respect to x, which would be 2y times dy dx, or y prime, and then times x to finish out the product rule.
Why are we
That's the
putting-
derivative of the left side. Say again?
Why are we putting the y prime again?
Because when you take the derivative of y squared with respect to x, you have to treat it like a chain rule. So you have to first bring the 2 down, then y to the first power. And then you have to take derivative of the y itself, which would be your dy dx or y prime.
Okay.
So here's what I would do. If that's confusing, come to my office hours or go look up implicit differentiation. If you want to go review some videos, I'm sure you can find stuff online. Implicit differentiation, Cal 1. And maybe you can find some stuff out there because this is absolutely an essential. We need this to be able to move forward. We have to have this in place. So you want to make sure you get it squared away before we get too much further ahead. Because like I said, at the beginning of this class, this train will leave the station without you. Like that's the way Cal 2 is. I mean, it's nothing personal. Okay, my job is to get through the material. But if there's something like a Cal 1 thing that you're not sure of, get it squared away as soon as possible. Because if we get so far down the road, you'll feel like you can't ever get back to us. So implicit differentiation. All right, at this point, I'm pretty much done taking the derivative. I just need to now figure out what y prime is at this specific point. And the point we're talking about is the point 0, 0. So that means I'm going to go to this equation. I am not going to go solve for y prime right now. I'm not going to go try and get y prime by itself. I'm actually just going to plug in 0 for x and 0 for y, because that's what I have here. So everywhere in this equation, let's replace x and y with 0. Boy, it's going to be real nice because it's going to kill all that off. So I'll just get 1 down there times, and then look at all this. What does all of this become? All the x's and y's are zeros, aren't they? Right?
Yeah, and they're multiplying. So would that even cancel? Yep.
Yep, it's all 0. Equals 1 plus y prime. What does the whole left side become?
1.
Well, 1 times what?
Oh, just 0.
0. Oh shit. 0.
1 times 0, so 0 equals 1 plus y prime. And now I'm going to subtract 1 on both sides. The slope of the tangent line at that point should be -1. Right? The slope of the tangent line should be -1. Now, that's not the equation of the tangent line, though, right? The original problem says find the equation of the tangent line. So this is where, again, in Cal 1, we learned that to find the equation, we use this formula, y minus y1 equals m times x minus x1. That was our point slope formula. We know the point we're given that this is 0 and this is 0. And we just found the slope of the tangent line to be -1. So if we replace everything here, we get y equals -1x, or y equals -x. That's the equation of the tangent line.
That was really neat. Could you theoretically do that with any like to find the slope, any derivative that you know what a point on it?
Yeah, absolutely.
Cool.
Yep. And I can verify it if I just graph it y equals -x, you can see it actually is the line that's tangent to that curve at that point. Okay, we are out of time. It's 12:40. We almost finished the notes. You have a homework assignment here. Let me see if that matches the. Yeah, pretty close. Let me just look at that real quick, see if that's, I want you doing all of that. I would say try everything except 39. 39, is a word problem, and I had not had an opportunity to show you. I was going to do this word problem here. I just didn't do it. So I think up through 39 should be, I mean, up through 32 here is, I guess, fair game. When you go to do your homework, what you're going to see is that it's a lot of just like practicing taking derivatives now that you have these new functions. See how it goes. Turn in what you can, right, by Sunday night, and reach out for help if you need it. I know that maybe you might, I know some of you might be feeling a little bit like, holy shit, you know, like, whoa. And, you know, don't panic yet, all right? But don't wait until you're too far gone for me to be able to help try and identify what you need to get caught up on. And that's going to require you come to my office hours. We talk about it. We work some things out. I know for a fact there are some of you in here that just implicit differentiation, you just have no idea how to do it. Okay. And so, you know, we just have to see if we can patch the holes. You know, we really need to see if we can.
A
All right, I'll meet
question.
you halfway. You meet me halfway and I'll help you. All right. I'll hang out.
Good question.
Actually, yeah, question. Go ahead.
For turning in that homework, do you want us to just do it the same way that we would turn in a test, take the photos and convert all into a PDF?
Yeah, just do it. Try and get it all to a single PDF and submit.
Sir, are you okay with me turning it in? So I do everything on my end.
Yeah, you can use your thing. Can you export it to a PDF?
I can. I
Yeah,
want
just do it that way.
like a digital.
Yeah, just do it. Export to PDF. You're using OneNote or no?
Yes, I'm.
Yeah, just export to PDF and then send that, and it should come out great.
Got it. Yeah, well, it's gonna be lined. It's gonna be squared, nice and neat.
Yeah, that'll work.
Yeah.
I have office hours right now that go, I think, for 30 minutes. If I'm not mistaken. So I'll hang out for a few more minutes if someone has a question, but I do need to jump over to my office hours. Someone's asking me, could you show us where to find the homework? So for the homework, you go to, where's my thing? You go to our course and you have to go to the ebook, which should be right here, ebook access, and then link to ebook right there. Now this has been hit or miss. You might have to create an account. It might let you in. Yeah, it's asking me to create an account, but that's where you get to the ebook, and then you just look at the problems off of the ebook. Did I show that in the orientation video?
Yeah, you showed it in the orientation video at the very end, or near the middle / end.
Yeah. Did you watch the orientation all the way, Audrey?
Yes, I did.
Yeah, just go re-reference it. I mean, it's there. Did you have a problem getting into the book?
No, I had the book last semester, so it just kind of like the website, so it just kind of worked pretty well.
Yeah. So you just go to the ebook and just pick the problems off of the end. I'm gonna try and log in.
Are we good to go?
Yeah, you're good to go. Yeah, you don't have to hang out. You're free to go. I'm just hanging out if anyone has any last questions. I do need to get to my office hours, but I'll wait.
Got it. See you on Monday, sir.
All right, have a good one.
One last question. You said on the orientation it shows us where like our homework problems are, right?
Mm-hmm.
Okay, all right. Just want to make sure.
Yeah, I mean, you get into the book.
Yeah, I already got into the book. I'm just like trying to figure out which problems we have to do, but that's all.
Oh, the problems are on the schedule.
Oh, okay. All right.
So on the schedule, it shows here today, and then it shows, now you can ignore the page, just pay attention to the section 3.5, problems 1, 5, 15, 16 through 28, 32. And I said to skip 39.
Yeah.
So that's where you go to figure out what you're supposed to do. Yeah, and then you go to the ebook. And so we're in chapter 3. I go to chapter 3. And there should be a menu here. Oh, it already took me 3.5, but there's a menu here. You can go to 3.5 exercises right there, and it'll take you right to the problems.
Yeah, I would have been better prepared, but I got hit with Corona for the past couple of days, so
I hear
why.
you.
Yeah.
I hear you. I know. It set me back too. But
All right, thank you, Professor.
all right, take care.
Thank you, sir. You have a nice rest of your week.
Yes.
All right. Have a good weekend, Professor.
You as well. Anybody want to come to my office hours? I'll be available there unless you have something very quick. I'm going to post in the chat my office hour link information if you're interested.
Do we just go ahead and join, or should
The
I
office
email?
hours? Did you get the
Yeah.
link? Yeah, go
Yeah.
ahead and join. And I have to close this out, of course, and then go join.
Oh, okay.
Okay,
Thank you.
so I'll do that right now. I'll meet you there. Give me a minute.
All right.